Hello, Science 8. Today we're going to talk about the states of matter. We're continuing on with chemistry from where we left off last week with density. So first little recap, what is matter? So matter is anything that has a weight, which we call a mass, and takes up space or volume. So weight, and then a volume is going to fill up a container. So mass, again, is the amount of matter that an object contains. You can see here that this object is very densely packed, so it's containing a lot of matter. So this would be related to its mass. So this might be a very, very heavy object, whereas this might be a lot lighter. So again, mass is the amount of matter that an object contains. Typically, we measure mass in grams. Volume is the amount of space that an object takes up. So liquids are typically measured in liters and milliliters, but solids are going to be measured in meters cubed, as we discovered last week. Again, as we kind of think about density, a volume, that's the size of this container. So this volume and this volume are the same in terms of the size of the container. This volume is different. But, for example, we can see that there's only 5 balls in this one and 5 balls in this one. This one is going to be more dense because it has more matter or mass for the given volume, versus this one is going to be less dense. So we only have 5 balls here, but they have much more room and they're spread out. So this is less dense than this is. Examples of matter, we talked about this last week. Matter's a very far-reaching thing. It kind of talks about everything that's solid, anything that's liquid, anything that's gas, and we're going to get into that a little bit more this week. Again, when we discussed matter last week, when we talked about density, mass, and volume, we were talking about physical properties. Next week, we're going to take a look at some chemical properties and look at some chemical reactions. So right now, we're still looking at physical properties. There's no chemical change going on here. It's just a physical reaction. We also talked about density. So again, density is the amount of matter or mass in a given volume. So something that has lots of matter or mass compact into a smaller volume is going to be very dense, versus a amount of matter that's not quite as tightly packed is going to be less dense. When we're talking about matter, we can also talk about states, which you may have talked about before in your other classes. There are 4 states of matter, 3 that you will be definitely familiar with, and 1 that you might not be familiar with. We've got solids. So solids typically hold their own shape. They don't change shape. They have a constant volume. Some examples of solid could be wood, silver, stone, or plastic. Liquids, on the other hand, take the shape of a container. So if I pour some coffee into a frying pan, it's going to take the shape of the frying pan. If I pour some coffee into a cup, it's going to take the shape of the cup. It always has a constant volume and surface. So if I pour 250 milliliters of coffee into my cup, it's going to be the same if I pour that 250 milliliters again back into the frying pan. So it has a constant volume, and it typically has a surface. So you can see here that the top of the liquid has flattened out, and that is what we're referring to as the surface. Examples: oils, juice, and gasoline. Gas typically takes the shape and volume of its container. However, it can be compressed. So that means that more and more of it can be packed in to be kind of squished together. So we can again measure the volume of gas. Plasma is the fourth state of matter. We're not going to talk a lot about it, but you should know that it does exist. It's very similar to a gas, but it doesn't have a defined shape or volume. And it has different electrical properties compared to gas. So if you're interested in that, I would encourage you to go research a little bit more about it. So the main thing we're going to talk about today is kinetic molecular theory. So the idea of kinetic molecular theory is a bunch of scientists made some observations about matter, and they created a theory about how matter behaved when it went from different types of temperatures. So kind of the main idea here is that this is a theory. So theory, you typically think like, oh, like it's just a guess. However, in science, a theory is not just a guess. It's something that's being proven through different experiments. So scientists have gone through the kinetic molecular theory for years and done different experiments to prove this theory. So you should feel very confident that what we're about to discuss isn't just a guess. It's been proven by science and gone through the entire scientific method many, many, many times. So all matter is made up of very, very small particles. So everything, I'm talking about your cat, I'm talking about your coffee cup, is made out of very, very small particles. And there are spaces in between those particles. So you can see here, spaces in between the particles. The particles are always moving, so they're not just stationary particles that make up all matter. And energy is what makes those particles move. So even though you can't see this, this is going on with every piece of matter that you're interacting with, from a glass of water to the glass that the water is in, to an ice cube, to a marshmallow. All of this is going on. Very, very, very small particles are making up this piece of matter. So energy affects the way these particles move. So when you add energy to matter, the kinetic energy of the particles increase. So when I add energy to matter, so energy could be something like heat. If I added heat to something, I could start to get the kinetic energy of the particles increasing and moving around more. And the particles begin to move faster and bump into each other more often, creating more space between them. So as soon as I add energy to matter, the kinetic energy, so kinetic energy is energy of movement, of the particles increase. So the particles get this energy added to them, and then they start to move because they have kinetic energy. As the particles begin to move faster and bump into each other, what happens is they need more space in between them. So the more and more energy that is added to them, the further and further apart they get. So this one's got less energy being added to it. This one's got more energy being added to it. So this kind of talks about the different states of matter. So when enough energy is added or removed from matter, a change in state can occur. So matter moves from different states. So for example, you can think of your ice cube moving. When you hold it in your hand, it melts into a liquid. And then eventually that liquid, if you sat there in the hot sun with it on your hand, it would start to evaporate into a gas. So this is what is occurring. So this is the kinetic molecular theory in action. So when energy is added, so in this case, we can think of energy as the heat from our hand or the heat from the sun. So when energy is added, it's going to change state. So when energy is added, it's going to move from that solid to that liquid to that gas. If it was removed, so if I stuck that puddle of water back in to the fridge, so if it gets really, really cold, so that heat energy is being removed, it's going to move back to a solid. So it's a very fluid thing. So these three states of matter are referred to as solid, liquid, and gas. And we're not going to talk about plasma because it's a whole different thing. So this is this idea of changes of state. You've probably talked about this before in science. So changes of state, so anything moves in this kind of different changes of state. So for example, chocolate. You had solid chocolate, you wanted to turn it into a nice kind of drizzle on top of something. You could melt that chocolate and move it from the state of solid into a liquid. Just like if you had an ice cube in the state of solid, you could melt it into a liquid. So each of these kind of processes has its own terminology, which I won't go over too much, but when a liquid moves from a gas, it's going through the process of evaporation. When gas is moving to a liquid, we're talking about condensation. So that's what's happening when it's raining outside, is we've got water is condensing. When liquid moves from a liquid to a solid, it's freezing. So we can think of that as a body of water turning into ice. And then the process from a gas moving to a solid is called sublimation, and then we've got deposition. So this requires a lot of energy to move this kind of far on the changes of state scale. So we won't go too far into that. We're really going to focus more on these two kind of aspects, but it all works on this kind of continuum, and it works with all different types of matter, not just water. That's just kind of the easiest example to use. So states of matter in the kinetic molecular theory. So KMT explains the properties of solid, liquids, and gases. So we'll kind of go back to the particle theory of matter after, but this is kind of why solids act the way they do. So solids, the particles are very, very, very close together. So you can see in my little GIF over here, the particles are very, very, very close together. And remember I said that they were always in a state of motion, so they move very, very so slightly. So they vibrate, but they don't move around, which is why when you look at a solid object, and remember these particles are very, 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 very small. When you look at a solid object, you don't see it moving or changing shape because it's only just kind of slightly vibrating. They're attracted to one another. So the particles have energy and it's attracted to the other particles. They want to stay together, which helps them keep this rigid structure. So if I poured a solid into a container, it's not going to take the shape of a container because they're not moving around very much. They're sticking very, very close together and they're very much attracted to each other. So they're staying in that rigid structure. So it doesn't take the shape of a container. Liquids, on the other hand, are a little bit different. So particles in a liquid, they are, again, very close together. So you don't see spaces in between the liquid. It's all kind of stays together as one unit. The particles are slipping and sliding past one another and kind of revolving around one another. So you can see they're kind of like slightly interacting and kind of moving close together. They're still attracted to one another, but they are attracted less so than solids. So what they'll do is they'll take the shape of the container. They'll just spread out a little bit more. So even though they're still very close together, they can spread a little bit more to take that shape of that container. Particles on a gas are very far apart compared to their size. So they spread out quite a bit. They move very randomly and quickly in straight lines. So they're moving all around a container. So if I have them locked up in this beaker over here, they're going to bounce around and take the shape of the entire container and really spread out. And if I opened up this beaker, they'd be gone. So their attraction to one another is really effectively zero, which is why they're able to spread out so much. So we'll go back to the particle theory of matter just so we can kind of reiterate it, because this is a little bit of a tricky lesson. So again, all matter is made up of small particles. So whether we're talking about a block of ice, a cup of water, or the steam that's coming off of that boiling pot of water that you put on the stove. there are spaces in between these particles. Even though we can't see the particles, they're very, very, very small. There is still a space in between them. The particles are always moving, though at different speeds based on how cold or hot or how much energy is being transferred to that particle. Energy, so heat energy is one of these things that makes the particles move, but energy in general can cause these particles to move, which is how we get those changes in state, moving from a solid to a liquid to a gas, is we're removing energy. So changes of state occur when matter transforms from one state to another. So when we get something moving from a liquid to a solid, that's a change of state. So liquid water to solid ice is an example. Here's just a summary. So solids, strong attraction between the particles. They're very, very tightly packed together, neatly arranged, and the particles are vibrating but staying in place. They always have a definite shape and a definite volume. So you can't take a solid object and change the volume of it unless you turn it into a liquid. It does not take the shape of a container. Liquids, moderate attraction between the particles. So they're kind of hanging out together, but not so as much as solids. Particles are still very close, but they're not neatly arranged. So they take the shape of the container. They slide past one another. They have an indefinite shape, so they'll take the shape of whatever container they're poured into. But they do have a definite volume. So the volume is not going to change. So if I have 50 milliliters at the beginning, I'm always going to have 50 milliliters. Gases. Very weak attraction between the particles. Particles are much further away from each other, so they're very spaced out. In fact, they'll take up quite a bit of space, as much as you give them. Particles move all around and bump into each other. Indefinite shape, indefinite volume, and it's going to fill and take the shape of the container. Changes of state and temperature. So two important temperatures of any substance. A melting point. So this is the temperature when the substance moves from the state of solid to liquid. So I'm talking about ice. So ice moves from a solid to a liquid at its melting point, which its melting point is 0 degrees. A boiling point is the temperature where a substance moves from its liquid state to its gaseous state. So if we're talking about water, we're talking about 100 degrees. So if you have a pot of water on the stove and you want to boil it to make craft dinner, you're going to have to wait till it's reached 100 degrees in order to add your noodles and to say that it's boiled. So what's really interesting about this is most people think of melting point and boiling point when they think of water, but all chemicals and all types of matter have a boiling point. So for example, gold's boiling point, if I wanted to make myself a fancy gold brick and I wanted to melt down the gold, I would have to get it to 2700 degrees Celsius to melt it. Or to boil it. Yes, to boil it. Not to melt it. So, quick little kind of discussion here. Not that we can have a discussion. I wish we could have a discussion. Why is there a gap on the railroad track? So you've got these railroad tracks. Another kind of quick question is, why are these pieces of metals on the deck of a bridge? So you can kind of see a close-up there. So possible reasons why we would want this. So what happens in the winter when it gets very, very, very cold is our metal is going to shrink just a little bit, because that whole cycle of changing states is on a continuum. So it's happening kind of gradually. So it's still going to shrink a little bit, even if it's still saying solid. So It's going to shrink a little bit in the winter, but in the summer when it gets hot, what's going to happen is all the particles are going to spread out, and that metal is actually going to expand. So what happens there is when this is expanding, it's going to take up that space in there. And if I didn't have that space in there, what would happen is the railroad track or the bridge would actually buckle and kind of bend out of shape because I didn't make any space for that contraction and expansion to occur. I'm going to skip this part. So when temperature increases, particles speed up. So when heat is added, particles are going to speed up. They move further apart from one another, and particles are going to occupy a larger volume. So they're occupying more space. So this is why it's going to get bigger, that piece of metal, when it gets hot outside. So this is known as thermal expansion. When temperature decreases, particles start moving slower. They're going to come closer together, and particles are going to occupy a smaller volume. So this is known as thermal contraction. So I'm going to show you the thermal contraction example and just a little bit of an example of changes of state. So I've got different types of matter that I can be using here. And what I'm going to use just to kind of show you is I'm going to use, not water. Water is a little bit more complicated. We can use water actually. Oh no, we'll use neon. Okay, so what I'm going to show you guys here is I'm going to show you guys an example of thermal contraction and expansion with this little model here. So I've got neon is the matter that I'm going to be using, or the element that I'm going to be using. So what I'm going to do is I'm going to change from adding heat to creating it cool. So I'm going to add energy and I'm going to take away energy. Okay. So let's get it back to its solid state. So right now it's neutral, it's solid. If I add some heat, what I'll do is the particles are going to slowly expand. Look at them slowly separating away from each other. They're starting to move faster. They're starting to take up the entire container as it gets hotter. Okay. My temperature, as you can see, it's in Kelvin, but it's going up. I can switch it to Celsius. So if I wanted to get neon to gas, okay. If I wanted to take away energy and bring neon back to its liquid form, I'm gonna have to go real cold, so minus 90 is what I'm at right now. So I'm cooling it down to see if I can get it to turn into a liquid. As you can see, so thermal contraction, the particles are slowing down, they're getting closer to one another, and they're slowly coming back together, so they're becoming more of a liquid. Clumping together, becoming more of a solid. Again, if I added energy, that'd be thermal expansion, so they separate out. Take away energy, thermal contraction, they come back together. So this is the same thing that's happening when we're talking about a bridge or a piece of metal.